we're going to prove that if the limit of f of x equals L and the limit of g of x equals m as x goes to a, then the limit of the product as x goes to a is just Lm. So proof. Let us think about what this means. The limit as x goes to a of f of x equals L. Now we know this truth. This is true. It's given. That means given any epsilon greater than 0, there does exist a delta 1 greater than 0 such that the difference between f of x and L is less than the given epsilon whenever the absolute value of x minus a is less than delta and x cannot equal a. X cannot be a. Now, what does this mean? The limit as x goes to a of g of x equals m means given any epsilon greater than 0, there exists a delta 2 greater than 0 such that the difference between the function and the limit is less than epsilon whenever the x value in absolute value is the x value and a in absolute value is less than delta 2 for positive. That just means x, the positive part just means that our x cannot equal a. So we have this. But I want it true for just one delta. So I am going to choose delta equal to the min, the least of those two. Okay. So I'm just going to recopy this line and this line, but I'm going to change just one thing. I'm going to call it delta. So f of x minus L is less than epsilon whenever this is true. And g of x minus L we get this statement for g of x minus L. The absolute value. Alright, so now, this is what we have to play with. Now, we want f of x times g of x minus Ln is less than epsilon whenever this is less than delta. Okay. So let us build that up. So let's see. F of x times g of x minus Ln in absolute values. Well, I want to get it to have f of x minus L. Oops, I do have one typo. That should be an M right there. So I want this last line to have f of x minus L and or g of x minus m. So that means I have to add 0 to it somehow. Because I want to add something and then subtract it, or possibly subtract and then add. for example, if I'm going to factor out what I write here, if I'm going to factor out f of x, then I want it to be minus m. So then when I factor it, I'll have f of x times g of x minus m. Something that I want. Okay, but I'm losing space, so let's write that a little bit smaller. This is equal to f of x and g of x, and out of nowhere I take away f of x m. Well, of course, let's do that in another color. So of course I have to add it back. I have to add back f of xm, and I still have to take away the ln. So those two are equal. I mean, I just added 0 to the right side of that equation. Now let's do what I said we were going to do. First, from here, we'll factor out f of x, and we get g of x minus m. That looks real good. Oh, look at this. Over here, when I factor out an m, I get f of x minus l. Looking very good. Looking very good. Now, this is less than the absolute value of this plus the absolute value of that. F of x times g of x minus m plus the absolute value of n times f of x minus l. But this is equal to the absolute value of the product. You can take the absolute values separately. Times the absolute value of g of x minus m plus m times the absolute value of f of x minus m. Okay. Notice up to right now, I never said, you know, whenever, you know, x minus a is less than delta. I didn't say that. But because what I have here, what I have below this, what I have below this line is true. It's always true. It's legal math. Okay, now we're going to start talking about something else. This is less than epsilon times, well, that's less than epsilon when x minus a, an absolute value, is positive and less than delta, plus m times O. That's less than epsilon. So I put something bigger than or equal to this. Now actually, this is strictly less than, because this piece is strictly less than delta. I mean epsilon. So I put something larger in the bottom line. And this piece is strictly less than epsilon. And I put something larger. But I can only put epsilon whenever 0 is less than x minus a, which is less than delta. Now, I can factor out the epsilon. And then I get the absolute value of f of x plus m, the absolute value of m. And this is true. So what we have right now is that this piece right there is less than or equal to this whenever this is true. Just starting to look good. What is this f of x? Okay, f of x might be really big. near A. Okay, I want this quantity to be small. So somehow I need to get a bound on f of x. So we do a little side work here. F of x in absolute value is equal to f of x minus L plus L in absolute value. But that's less than or equal to the absolute value of f of x minus L plus the absolute value of L. But this is less than epsilon plus the absolute value of L whenever x minus a is positive and an absolute value is less than delta. That is, I can't put epsilon there unless this is true. Okay, but we want that statement to be true. So this is coming down. This is equal to epsilon times epsilon plus the absolute value of L plus the absolute value of M whenever 0 is less than this mess, which is less than delta. Okay, now I don't like this epsilon. I only want it to have one epsilon. So what I'm going to do is I am going to choose epsilon to always be less than or equal to 1. Okay. So I want to get something bigger than that. So here's epsilon times this. Well, if over here I write something bigger than this, then this sign is right. Well, here's the L plus M, and here I'm going to put something at least, well, this is less than or equal to, I'm going to put something at least as big as epsilon. 1. Okay, and this is whenever this is true. Okay, so now let us see what we have. We have that f of x times g of x minus lm in absolute value is less than, because at some point we had less than, it's less than epsilon whenever this is true. Oops, epsilon over, no, need some more space. We showed that f of x g of x minus lm is less than this, less than epsilon times 1 plus L plus the absolute value of M whenever this is true. If I divide by if I divide by 1 plus L plus M on both sides, this piece shouldn't change. That is 1 over 1 plus L plus M 1 over 1 plus L plus M, absolute value of M, times this, f of x, g of x, minus Ln. This is less than epsilon whenever that's true. But this here is the same as 1 over, now this quantity I'm writing is positive, so I don't need to put absolute value below. Well, actually, it doesn't matter. So I'm going to distribute it times f of x, g of x, minus 1 over, yes, 1 plus L plus M times Ln. Ln. And this is less than epsilon when all of that is true. This here is one quantity minus another quantity. Let me just write it right above because I really don't want to lose the continuity here. Now, other people would define epsilon to be a little bit different, but I'm going to stay with this. So, this statement right here, you know, what goes here is whenever 0 is less than the absolute value of x minus a, which is less than delta. That whole statement tells me that the limit as x goes to a of what I had circled in blue equals that. That shows me that the limit as x goes to a of 1 over L plus the absolute value of M times f of x, g of x is equal to 1 over 1 plus the absolute value of L plus the absolute value of M times Ln. The limit of this equals that. Okay? But now, this right here is a constant. I can move it out in front. That is 1 over 1 plus the absolute value of L plus the absolute value of M times the limit as x goes to a of f of x, g of x is equal to 1 over 1 plus the absolute value of L plus the absolute value of M times Lm. Well, multiply both sides. Well, you know, just cancel that. So you get the limit as x. Now this bottom is positive, so we're not dividing by 0. It's at least 1. L can be 0, M can be 0, but 1 is 1. The least it can be is 1 because the absolute value of L is 0 or more. The absolute value of M is 0 or more. Okay, so we get the results that we need. It equals to L. That concludes this proof. See you in the next